Hello, you absolute legends. My name is Eric J. Choi, and I'll be explaining Section 5 Explainer Video 3.2, which talks about an oscillating system in which there's a damping force that causes the amplitude to go down with every oscillation. And jumping right in. Problem 68. An oscillator with a mass of 500 grams and a period of 0.50 seconds has an amplitude that decreases by 2% during each complete oscillation. If the initial amplitude is 10 centimeters, what will be the amplitude after 25 oscillations? And attached right here is a diagram what I think this damped oscillation system would look like. As you can see, it goes up and down to a certain amplitude, but after each oscillation, the amplitude decreases until it slowly and surely gets to a plateau of an ultimate ending final value of 0 after a supposed infinite amount of time. Now note, if there was no damping force, then just like a simple harmonic system, it would just constantly go to the same amplitude on and on forever. Note that this is going down because there is a damping force such as friction, or as time goes by, some of the energy is not conserved and gets converted to thermal energy instead. Now note, there is two approaches to solving this problem. You could arrange the 1-all-be-all equation of A times cosine omega t plus phi, which is adjusted for damped oscillation systems, such as this one right here, which includes B, the damping constant, times T over 2m, to the exponent power. But there is a much easier and simpler way to solve this problem if you read the problem carefully. Now note that it gave us a lot of statistics, such as 500 grams for the mass, a period of 0.50 seconds, but most importantly, an amplitude that decreases by 2% during each complete oscillation. So technically, we can solve this problem by disregarding everything except the amplitude decreased by 2% after each oscillation, there being 25 oscillations, and a period being 0.50 seconds, as seen right here. To find the amplitude after one oscillation, all we need to do is multiply the initial amplitude by 98%, which is 100 minus 2%. So it ultimately ends up being 0.98 times A initial. If you're trying to find amplitude after the second oscillation, it's the exact same thing, except we replace A1 with A initial from the previous step. So once again, it's 0.98 times A1. But note, A1 is equal to 0.98 times A initial. So these 0.98s combine to become 0.98 squared for this amplitude after the second oscillation. I'm thinking you can see the pattern here now. So, to find the amplitude of the 25th oscillation, we have to find 0.98 to the power of 25 times A initial. And our A initial, as shown at the very top of the problem, is 10 centimeters. So 0.98 to the 25th power times 10 centimeters is equal to a final answer of 6 centimeters after rounding it. Now I think these kind of problems are very important because there are multiple ways of solving a problem, and I'm pretty sure that each way will end up with the right answer, but there are simply smarter ways of solving problems as well that will save you much more time in the long run, and it may actually help you find shortcuts on future classes where you have exams that have limited time. I hope you guys understood this problem, and thank you for listening, you absolute legends.